Hi everyone and welcome back to NTE. In today's video we'll be looking at multiple choice questions from the National Past Exam Papers. Again we're going to be looking at November 2014 all the way up to 2020. Okay. Specifically today we're concentrating in the section of electrochemistry. So let's see what can we learn from these multiple choice questions. Right. So starting us off with November 2014. Question 1.3 says, consider the reaction represented by the balanced equation below. Right, we've got a reaction between solid copper and some silver ions in solution. Okay. The question is, in the above reaction, the solid copper is what? Okay, so basically we're looking at this solid copper, and if you notice, it goes from being solid copper to being copper 2 plus ions. Right, now we used to learn that if you lose negativity, right, you become more positives, and by negativity we mean electrons. Okay, so you can see that the copper has basically become more positive, right? It went from being or having an oxidation number, if you want to speak technically, of 0 to +2. So it basically lost electrons, right? Why do we call the loss of electrons? Well, it's oxidation. Okay. And which species undergoes oxidation? It's always the reducing agent. Okay, so this section of electrochemistry is unfortunately very theory intensive, so you do need to know your theory. Okay, all right, so now let's check the options. The copper, right, option A says is an oxidizing agent. No, it's not. Oxidizing agent. No, it's not. C says reducing agent. Okay, so we're getting somewhere. Reducing agent and is reduced. No, remember it can't do exactly the same thing. So our answer is D. It is a reducing agent and it is oxidized. Remember this word oxidized means to lose electrons. Okay, starting us off nice and easy. The second question, 1.9 for November 2014, then says, an electrochemical cell, right, is used to electroplate, right? So you should know basically what electroplating is. It's all about coating a metallic layer onto another cheap metal, right? And you should have your theory now running in your head that this is an electrolysis process, right? So we're going to be converting electrical energy right to chemical energy. Or in other words, we're going to use electricity to drive a non-spontaneous chemical reaction. Okay. All right, let's read on. They say to electroplate an iron spoon with nickel. Okay. Now, which one of the following half reactions takes place at the positive electrode of the cell? All right. Now, let's just quickly remind ourselves the setup over here of electroplating. Obviously, we need a battery. Okay. And now we're saying what is happening at the positive electrode, right? The electrode that's going to be connected to the positive end of your battery is always going to be the anode. Okay, and then the one that is going to be connected to the negative end of your battery is going to be the cathode. Okay, now theory on electroplating. Whatever you want to plate, the thing that needs to be plated is always placed at the cathode, right? So let's just read this again. They say to electroplate an iron spoon. Okay, so over here we're going to have the spoon. Nice drawing of the spoon, eh? Okay, so this is where the spoon is going to be, and then on this side we're going to have a solid piece of nickel. Alright, so that's it. Just a rough schematic of what's going on. And now let's go back again. We're looking at the positive electrode. Okay. Now the positive electrode is the one that is connected to the positive terminal. So here at the anode, what happens at the anode? That doesn't change whether you're looking at a galvanic cell or an electrolytic cell. The process that happens at the anode is always oxidation. Okay. So over here, we're going to see oxidation. Oxidation of what? Oxidation of this solid nickel. Okay, so we basically have to go through all of our equations here, and all these ones with the iron is obviously out. We have to find the one that has the nickel, and we said we want to see oxidation of nickel, so our answer has to be option D. Okay, because that's the one that is releasing electrons. Remember, oxidation always releases electrons, right? Or loss of electrons. Okay. Right, so moving swiftly along to November 2015, okay, we now have question 1.9, which says that the following half reactions take place in a galvanic cell, right? So that's important for us to know that over here what we're looking at is a galvanic cell. Okay, now let's just quickly look at these reactions. Note that these reactions both have the gain of electrons, okay? So basically what these reactions are written as is reduction reactions, okay? But of course we know for a galvanic cell to actually work, one of these reactions has to be a oxidation, okay? Now it says, which one of the following is the cell notation of the cell, okay? Well, unfortunately, we can't really answer this question just based on what they've given us, but there is another resource that we're given that you should always know about, and that is your table of standard reduction potentials, right? So basically, we have to go find these two equations, half reactions, sorry, in that table in order for us to see which one is above the other, and then only can we come back and look at the cell notation. Okay. All right, so here we are in our table of standard reduction potentials, and to find the equations, you just have to look quite carefully, and I can already find the first one over here, the cobalt one. Okay, and the other one that we're looking for contains aluminium. So aluminium 3 plus ions. Just move down. Aluminium 3 plus ions. There they are over here. Okay, so quite a distance from each other, and basically, like I've explained before, if you look at this, you are seeing a strong oxidizing agent to the left and up. So our cobalt 3 plus ions are our strong oxidizing agents, and to the right and down you're looking at the strong reducing agent, so that is going to be our aluminium. All right, so now the reducing agent is always the one that undergoes oxidation. Okay, so this is the oxidation half reaction. Okay, and it is necessary for us to recognize which one is going to be the oxidation half reaction, because we need to figure out which reaction is happening at the anode and which reaction is happening at the cathode. Right, so now that we have all this information, we can now take it back to the question. Alright, so I've written now our two reactions, basically in the right order, where one of them is specifically the oxidation one and the other one is the reduction one. Okay, so we need this. Okay. Alright, so basically now another thing that you need to know is how do you set up your cell notation. Okay. Right, so both of these things, not actually both of them, one of them is an ion. Okay, if you look at our cobalt, we're looking at cobalt 3 plus ions and cobalt 2 plus ions. Okay, so now because we have an ion in one of the reactions, we need a surface onto which that ion can then interact with. Okay, and whenever we need a surface, it means that we need an inert metal, which is always going to be platinum, right? So that immediately cancels out this option because there is no platinum, and cancels out. Okay, it doesn't really cancel out this option because the platinum is over here, but let's just keep it for now. All right, now something else. The structure of cell notation is always what happens at the anode, then we have a salt bridge, and then what happens at the cathode. Okay, so the cell notation is basically sort of like a story. Okay, so we're now going to check. We know that at the anode we have oxidation at the anode, right? So looking at our oxidation half reaction, all that we need to see in the cell notation is this solid aluminium going into aluminium 3 plus ions. Okay, that's all that we need to see. We don't need to see the electron. Okay, so now if you check B, you have solid aluminium, aluminium 3 plus, solid aluminium, aluminium 3 plus, and now here comes the problem. In D, this first part has to talk about what is happening at the anode, right? So we can't start the cell notation by talking about what is happening at the cathode, so immediately now that cancels out option D. Okay, so we're moving along nicely. We're now stuck with option B and C. We only have two things to work with. Okay. Right, so now we have our salt bridge. There we see both of them have a salt bridge. Now at the cathode, we have reduction happening at the cathode. And for the reduction, we want to see the cobalt 3 plus ions going into cobalt 2 plus ions. Okay, so it all just comes down to the order over here, right? 3 plus first and then 2 plus. Okay, you can see it there, 3 plus and then 2 plus. So our answer is option B. Okay. All right, so still in November 2015, question 1.10 then says, chlorine gas, right, is bubbled into a potassium iodide solution. Okay, the reducing agent in this reaction is, okay, so there's a few key words over here. We have this word that says solution, okay, which means these two things are in aqueous form or aqueous state, right? And they want to know which one or which species is going to act as the reducing agent. Okay, now just quickly draw from your theory, the reducing agent always undergoes oxidation, right? It doesn't matter whether are you looking at a galvanic cell or an electrolytic cell, the reducing agent always undergoes oxidation. Okay, all right, so our options are either potassium ions, the chlorine gas itself, the iodine ions, or the chloride ions. Alright, so believe it or not, what can help over here, instead of us trying to guess, is to actually use our table of standard reduction potentials, okay? Because we can also use that table to identify reducing and oxidizing agents. So we're just going to go searching now on that table to find these 3 or 4 members, right? And we just want to see which one is the strongest, right, reducing agent, because then the strongest one is the one that will undergo oxidation. Okay, so let's go to our table. Alright, so on table 4A, what I've done now is I have basically identified all of these 4 components, right? And now you just need to remember how this table is structured. Okay, so remember that on the left hand side, that is where you're going to find your oxidizing agents, right? And then here on the right hand side, that is where you're going to find your reducing agents. Okay, so now immediately certain things are out. Okay, the chlorine gas itself as a reducing agent is out because it is on the oxidizing agent side. It's an oxidizing agent. Okay, and if you move down, the potassium ions are also out because they are oxidizing agents, not reducing agents. Okay, so now looking at the table now, looking at the reducing agent, it comes down to between the chloride ions and the iodine ions. And remember, I am looking at table 4A, right, which basically lists all of these standard reduction potentials in decreasing order, right? So the strongest oxidizing agent is always at the bottom of the table, right? As you go down the table, that is where you're going to find the strongest oxidizing agent. Or you can just use my direction arrows like that. Okay, strong oxidizing agent, strong reducing agent. You can see it's pointing downwards towards the iodine ions. Okay, so that is going to be the one that will undergo the oxidation. Okay. Right, so then coming back here to answer the question, it is then simply just option C. Okay. Right, now going to November 2016, question 1.9 says, which one of the equations below represents the half reaction occurring at the cathode, right, of an electrochemical cell that is used to electroplate an object? Okay. Now, this is again going to be from theory. You need to know your electroplating quite well. And you also need to just quickly remember that the cathode is always at the negative terminal, right? Because electroplating uses electrolysis, right? So at the negative terminal, that is where you, okay, I don't need an arrow there, sorry. Okay, so at the negative terminal, that is where you're going to find your cathode. And if you want to electroplate something, you always attach that thing that you want to electroplate on the cathode. For example, the spoon that we were looking at previously. Okay, that's going to be on this. I should really learn how to draw a spoon, okay, because that is a very ugly spoon. But we'll leave it. Okay. So the object that needs to be electroplated always gets attached to the cathode. Right. So what is the question here actually? They're asking which one of the equations represents the half reaction occurring at the cathode, right? Okay, so the reaction that always occurs at the cathode is the reduction half reaction. So we just need to see if any of these equations or reactions are giving off electrons, and then we just quickly cancel them out, and I can already see I can cancel out A because it is an oxidation reaction. Okay, so that's out, right? So reduction, gain of electrons. Right? So there you see a gain of electrons, gain of electrons, gain of electrons. Okay, so now we need to think a little bit more. All right, so to electroplate means, right, to cover with a metallic layer. Okay. Now, this is now what is going to cause these other equations to disappear. I cannot use this equation because it's just forming ions, right? These two things are not metals, right? So I cannot use those two to electroplate, right? So by means of elimination, our answer is B. Right, now moving on to November 2017, right, and we're now looking at question 1.8. It says the cell notation of a galvanic cell, important, galvanic cell, okay, is given as follows, right? Now you are given the cell notation, which means you still need to understand the fact that what is happening this side is the anode, and then you have your salt bridge, and then what's happening on this side is the cathode. Right, so if we check over here what's happening, you basically have a nickel anode, right? And then the solid nickel is being oxidized, right? Oxidized into nickel 2 plus ions, right? Okay, the electrons are going. When they get to the cathode, right, they then get reduced, or they reduce, sorry, the lead 2 plus ions into solid lead. Okay, all right, so let's see. They say which one of the following statements is correct. Okay, nickel is oxidized. Yes, it is. Okay, you can see there nickel is oxidized. That is correct. Lead solid is reduced. No, lead solid is not reduced. It is the lead ions which are reduced. Okay, so this part is what makes it wrong. And then they say nickel 2 plus is the oxidizing agent. That's not the oxidizing agent. The oxidizing agent is the substance that gets reduced. So this over here is the oxidizing agent. Okay. Right, so this is also wrong. And then we have lead 2 plus ions is the reducing agent. Let's just see. No, like I said, lead 2 plus ions is the oxidizing agent. Okay. Alright, so that confirms for us quite nicely that the answer here is going to be A. Right, question 1.9 from November 2017. Right, then says, which one of the following combinations correctly shows the products formed during the electrolysis of a concentrated sodium chloride solution? Okay, so let's just write a few things down here. Sodium chloride. Okay, so we want to find out which ones are the products. Okay, all right, again, this is going to be a theory question. You just need to be familiar with the setup of the electrolysis of concentrated sodium chloride, and when you know that, basically you understand that the sodium is a spectator ion within that entire electrolysis, right? And the products that this electrolysis forms, it always forms hydrogen gas and chlorine gas. Okay, so the electrolysis of concentrated sodium chloride always forms hydrogen gas and chlorine gas. Okay, all right, so let's look at the options. If we just quickly ignore this cathode anode situation, I am seeing the sodium in two of the options, which means that they are completely out. Right, I can eliminate those two options immediately because I see sodium. Right, okay, now I'm left with the two options that have the hydrogen and the chlorine swapped around. So now I need to decide which product is going to go where. Is the hydrogen going to be at the cathode, or is it going to be at the anode, or vice versa? Right, so now for this we can also just use some common sense without actually redrawing the entire experiment. We just need to understand again that because we're looking at electrolysis, right, which is an electrolytic cell, the cathode is attached to the negative terminal of the battery, and the anode is attached to the positive terminal of the battery. Okay, so now that means, remember this is a spectator ion, so I don't need to look at it. So looking at the chlorine ions, you can see chlorine is negatively charged, the negatively charged ions will always get attracted to the positive terminal or the positive electrode, right? So which means I'm looking for the option whereby I have the production of chlorine gas happening at the anode, and that is going to give me option B. Alright, so that was just basically a nice theory question, but you could reason yourself through it as well. Right, November 2018 then says, consider the cell notation for the galvanic cell below. Right, again, we're looking at a galvanic cell. Right, and again, we're looking at solid nickel, right, at the anode being oxidized into nickel 2 plus ions, and then you should actually recognize what this is. This is your standard electrode potential, right? Or sorry, let me say it again. It's the standard hydrogen electrode. Okay, so the She cell. Right, and you have it connected to the cathode at the moment. Right, so your standard hydrogen electrode is currently in the cathode mode, right? So in other words, the hydrogen plus ions are being reduced into hydrogen gas, which is bubbling out. Okay. All right, now it says, which one of the following half reactions takes place at the anode of the cell? Okay, so now we can see at the anode, we see the oxidation of nickel solid. So that's all we have to be looking for. A nice one, actually. And this one is out because it's looking at hydrogen. This one is also out. And then this one is out because it is a gain of electrons. We want the reaction that happens at the anode is always oxidation, which is a release of electrons. So our answer here is D. Okay. Then 1.9 then says, which one of the following is applicable to an electrolytic cell? Okay, nice theory question. Let's just see. All we're thinking about now is our electrolytic cell. Okay, let's run through these. Option A says, reduction takes place at the anode. What always happens at the anode? Oxidation. Okay, so this is wrong. Oxidation takes place at the cathode. No, again, what always happens at the cathode? Reduction. Okay, so that's wrong. It uses alternating current. No. We never ever use alternating current in electrochemistry because we're trying to achieve something here. Alternating current is just going to make the electrons move in circles and we're not going to get anything done, right? So that's wrong. We actually use a direct current, okay? All right. So by default, the answer is going to be D. A battery is used for the cell to function. Okay, and that is absolutely correct. Right, now on to November 2019. We have 1.8. Two hypothetical half reactions and their respective reduction potentials are shown below. Okay. Right, so the nice thing about this one is that the standard cell potentials are given right on the side of it here. And in any case, they said it is hypothetical cells, so you could not go to your table to go try and find these ones. What they're now trying to test here, okay, is your understanding that the more negative, right, a standard cell potential is, right, the more likely that that half reaction will undergo oxidation. Okay, because remember we're saying that these are reduction potentials, right? So a negative standard reduction potential basically tells you that this half reaction does not, under natural circumstances, actually want to undergo reduction. So in fact, it's going to undergo oxidation. So it's going to go this way. Okay, so this is going to be our oxidation reaction, and then this one is going to be our reduction reaction. Alright, so they go on to say that a galvanic cell, right, is set up using the above substances. Okay, now it says which one of the following statements is correct for this galvanic cell. Okay, basically now we just need to add a few more things here. Because this is the oxidation reaction, it's happening at the anode. And then because this is the reduction reaction, it's happening at the cathode. Right, now let's do just a little bit more. Okay, all right, so if you never knew, your reducing agents and oxidizing agents are always reactants. Okay, so now if we start with this oxidation half reaction, going that way, the B solid is a reactant. Okay, now what undergoes oxidation? The reducing agent. Okay, so a reducing agent undergoes oxidation, and then it's going to be oxidized into that, right, the B plus ions. And then if we look at the reduction half reaction, here is the product, right? Obviously I cannot be looking at the electron, so the A plus is the oxidizing agent. Okay, and oxidizing agents always undergo reduction. That's how I identify that that is the oxidizing agent, and it gets oxidized into the solid A. All right, so now we can at least start looking for the correct option. Option A says B solid, right, is the reducing agent. Yes, it is, most definitely. Okay. A solid is the oxidizing agent. No, it's not. Like we identified, the A plus ions are the oxidizing agents, and how you basically get your head around that is just to remember that oxidizing agents and reducing agents are always reactants. Okay. The mass of B solid will increase. No, it most definitely will not. It will decrease since it is being oxidized. Okay. It will eat away or erode away or whatever you want to say. Okay. The mass of a solid will decrease. No, it's not. In fact, it's actually going to increase. All right, so that's wrong. Confirming very nicely for us that the answer here is A. Right, so November 2019, still question 1.9 should be an easy one, looks like a nice theory one. It says in an electrolytic cell, now concentrate, electrolytic cell, start getting your theory in your head, right? Let's see. Option A, the anode is the positive electrode. Yes, indeed it is, okay? Oxidation takes place at the cathode. No, it does not. Oxidation always takes place at the anode. Okay. Electrons flow from the cathode to the anode. No, they do not. Electrons flow from the anode to the cathode. The mass of the anode increases. No, it does not. Okay. The mass of the anode decreases. Okay, so think of something like electroplating. You always then put the substance that you want to use, the metal that you want to use to plate with at the anode, and the anode basically undergoes oxidation, so it's going to decrease in mass over time. Okay. All right, so yet again confirming for us that our answer here is A. Right, so moving on to November 2020, we have Question 1.8 says, which one of the following reactions will proceed spontaneously under standard conditions? Alright, so now just need to highlight something. If we use table 4a, okay, the way that we spot or identify a spontaneous reaction is to have a reduction reaction happening above an oxidation reaction. Okay, and also remember that in order for a reaction to happen spontaneously, it has to be a reaction between a strong oxidizing agent and a strong reducing agent. Okay, right, so they were quite mean in this question because each and every one of these reactions are different. So we're going to have to compare them slowly but surely, one at a time. Okay, all right. Now, for the people that use table 4b, if you're using table 4b, this condition still holds, right? You're still looking for a reaction between the strong oxidizing agent and a strong reducing agent, but in table 4b, this is going to be in reverse. Your oxidation is going to be above the reduction, okay? But I'm using table 4a, so I want to spot that over there, okay? Right, so let's go over to table 4a. Right, now I'm going to rewrite the equations over here. Option A says, alright, so here's the equation for option A. It is nickel plus ions reacting with hydrogen gas. Okay, so we can go to this table and find those two components. Here's hydrogen gas, okay, together with the H plus. Also just concentrate on the product side. And then you have nickel 2 plus ions. Right. Okay. So those two things. Now I want to identify, are these two reactants strong or weak? Okay. So if I draw my direction arrows, I know that the strong oxidizing agent must be on this side. Okay. So which means this one is actually a weak oxidizing agent. Okay. So I cannot use a weak oxidizing agent if I want to get a spontaneous reaction going. Okay. So already option A is out. Alright, now for option B, we're looking for bromine. Okay, so in this table we must find bromine. Okay, there it is, which is reacting with chloride ions. Okay, reacting with chloride ions, there's the chloride ions. Okay, now let's see what's the relative strengths. The strong oxidizing agent is going to be the chlorine gas. Unfortunately, that is not what I'm using as my reactant. So if I look here, going to the right and down, right, on this side, this is actually a weak reducing agent. Okay, so immediately when I find something weak, I cannot use it to do a spontaneous reaction, so option B is out. Alright, now let's try to find the components of option C. We're looking for Fe3 plus together with Fe2 plus, and that's going to be this one over here, but we're concentrating on the Fe3 plus. And then we're looking for iodine. Okay, there it is. Right, and our reactant is this iodide. Okay, right, so let's draw my direction arrows. Okay, strong oxidizing agent to the left and up. Yes, definitely that is a strong oxidizing agent. And then if I go to the right and down, I find my strong reducing agent. Okay, so there we go. We've got our answer. Our answer is going to be option C. Okay, let's just check option D just to be sure. Alright, so for option D, you're looking for copper plus ions together with copper 2 plus ions, and that's going to be this reaction over here, but we're focusing on the copper plus ion. Okay, and then you're also looking for lead with lead 2 plus ion, and our reactant here is the lead 2 plus. Okay, now if you draw your direction arrows, you can see that if I go to the left and up, I find nothing that I've circled, which means that this one is a weak oxidizing, not oxidizing, it's a weak reducing agent. Okay, it's on the right hand side. Okay, so again, like I said, the minute you find something weak, you cannot create a spontaneous reaction with that. So that is why option D is also out. Okay. Alright, so then finally, question 1.9, November 2020 says, the simplified diagram below represents an electrochemical cell used for the purification of copper. Okay. Right, so this is going to be a theory question, so you must be able to now recall your theory on the purification of copper. Right, the first thing you must recall is that in order to purify copper, we use an electrolytic cell, which means that you have to see this battery, okay? And then because it's an electrolytic cell, the negative terminal is what we call the cathode, and the positive terminal is what we call the anode. Right. Again, another theory for the purification of copper, you always put the impure copper at the anode so that it can undergo oxidation, okay, so that it can be oxidized into copper 2 plus ions, right? And then every time that happens, a copper 2 plus ion that is in solution gets reduced on the cathode, right? What is the actual question? Question says, which one of the graphs below represents the change in mass, okay, of the electrodes P and Q during the purification process? Well, based on what we just talked about, we can see that electrode P is going to increase in mass, while electrode Q is going to decrease in mass. Okay, so now we're going to go to our graphs, and we're just going to focus on one of the electrodes. I'm going to focus on electrode P all the time, and I want to identify the graphs that actually show that over time I'm seeing an increase in the mass of electrode P. Okay, so I can see for graph A, yes, I can see an increase in mass, so that's fine. But for graph B, I see a decrease in mass, so that is out. For graph C, I see an increase in mass. For graph D, I see a decrease in mass, so that is out. Okay, now let's quickly zoom into graph A and C. There's a slight difference between the two. Okay, and the difference is at this coordinate over here, right, or basically where the graph starts. Graph C, if you can see, it starts exactly at the coordinates 0, 0, okay, which is trying to say when time is 0, right, or at the beginning, electrode P has a mass of 0. But does that actually make sense? No, it doesn't, because at a time of 0, if you look at the sketch, okay, or at the beginning, if I can put a switch over here, for example, okay, and we pretend that the switch was open, right, that could represent a time of 0, right, or at the beginning. And at the beginning, electrode P actually does have a mass. This is pure copper, right? This is an actual piece of pure copper. So at the beginning, electrode P actually has a mass, so that now disqualifies graph C. Okay, so graph C is out, and our answer is going to be graph A, which is telling us that at time 0, okay, we have some mass, right? There's some initial mass of P, which is basically the mass of electrode P. All right. Okay, so then that brings us to the end of today's video. What we've done is we've looked at all the multiple choice questions, right, from the section of electrochemistry, right from November 2014 up to November 2020. I hope you guys enjoyed this video and actually learned something, and I will see you next time.